Hi everyone, and welcome to this quick recording for astronomy class. Today is November 7th, and we are still dealing with, now we're introducing actually new concepts. We're dealing with units 51 and 52, and actually we're probably going to cover all the way to 54, depending on how it goes. So I'm not sure, honestly, if we'll be able to, because of the fact that this week is an important week in terms of examination. We have midterm 2 this Wednesday, which brings me to a point that is very important. I know a lot of you did not do the review yet. The review is still going to be available for another day. Tomorrow afternoon is going to be basically the last opportunity for you guys to to do the review for the exam. Now, the review itself is graded, so you must do it. I mean, otherwise you're going to get 0 in it, and I hope that you don't do that. You will get full credit the minute you submit it, meaning that you have basically tried at least to prepare for the exam. Therefore, you're going to get full credit for it. The midterm is on Wednesday, and it's open from 8 o'clock in the morning till like 11 p.m. I will be available basically the entire day for you guys on that day, just in case if you're into an issue or something. Give me probably maybe about half an hour at most, and I should be able to reply to you. So it should be a lot less than that, hopefully within minutes, because I have another class also that is also doing an exam on that day. So I may not be available, but I will let you know immediately when to get back to you. So it should not be more than that. It should be less than half an hour actually, where I could reply to your request. So, but I'm available the entire day. Now, if you are working in the daytime, or if you have classes in the daytime, you still have the later on in the in the day, namely early in the evening, to take care of the exam. If it's the other way around, where you're busy at night, or you have other classes at night, or you have work at night, then you still have the daytime to take care of it. So there should not be an excuse. I'm hoping that you guys will have plenty of time to go through the actual exam on Wednesday. But before doing that, you really must do the review for 2 reasons. First of all, it's a graded assignment, meaning that if you don't do it, you're not going to get any marks for it, and that's going to affect your grade. You don't want that, really. And the second reason why you would want to do it is actually because it helps you prepare for the exam. This time is a little more material, so there are more questions basically to prepare for. So you really need to spend more time on it, okay? The next exam is actually longer than this too, in terms of content. So it's more content for the midterm 3. So I'm hoping that you guys would basically move on to completing this one actually tonight, if not be. The worst case scenario is tomorrow. So this is in terms of the exams. In terms of the content, this content is not related to this midterm. So this is actually part of midterm 3. So we're starting with the sun. We're going today to discover a little bit about the sun. We're going to get into its core to see how basically what's happening in its core and how it generates all of that energy. So those are the 2 topics of the day. Everything is on Canvas. So let me get into the notes of today. Let me share. And it's unit 51. So again, unit 51 deals with the sun and basically what keeps it going, okay? Because there is tremendous nuclear reactions in its core. Those nuclear reactions generate a lot of heat, so it really should be exploding. And it's an explosion. It's really a nuclear explosion all the time, every second and everywhere in the sun, at least in its core. So why it's not dissipating, why it's not flying every which way? Well, there is another force at stake, namely the force of gravity. The force of gravity is trying to collapse that material on itself. And the 2 now reach a balance, reach a thermal equilibrium, if you wish, between these 2 forces. So you have 2 forces at work in this case. An outward force, an outward pressure coming from the heat that is generated in the core of the sun, and an inward pressure due to the force of gravity, and these 2, they reach a balance. So right now, the sun is okay. Right now, the sun is not growing in size and not decreasing in size. And it's going to last for another 5 billion years, basically, okay? But then after that, it will start running out of fuel in its core, So in that case, it's going to basically, initially it's going to start to shrink a little, but in doing so, its temperature actually increases, causing the helium actually in it to burn. And as it burns, now it generates more energy, and then the sun swells in its shape. As it swells, its outer layer will get actually cooler with respect to the inner ones. So it's going to go through a red giant stage, and then it's going to actually go through a lot of the stages. First of all, consuming the hydrogen in its upper shell outside of the core, and then the shell outside of the core, and then the helium inside the core, and then process continue through several stages, and until at the end there will be nothing left but the gas that is going to escape, namely the cloud that forms in this case, which is a nebula, and then the core will collapse on itself into a white dwarf. So this is in a nutshell what's going on in the sun. For right now, it's maintained. It's not increasing in size due to the pressure, and it's not decreasing in size due to the gravity. So it's really the perfect equilibrium, okay? Increase a little bit in size because the temperature is higher, so it's going to cool enough. When you increase in size, the volume increases and the pressure diminishes. As the pressure diminishes, now the temperature lowers, and because the temperature lowers, the gravity will push it further. As it pushes further, now there is more chance for nuclear reactions, which will cause it to expand. So it's really sitting where it's supposed to be right now, okay? And then because the sun is mainly gas, okay, it's mainly hydrogen gas, actually. The two essential elements in the sun are hydrogen and helium. If you look at the periodic table, those are the two first elements in the periodic table. Okay, so I have a periodic table in here. Here I have hydrogen. That is the lightest element in the periodic table. On the opposite side of it, you have, or do I have it backward? Yeah, this is hydrogen. On the opposite side, you have helium. Okay, you have helium in here. Okay, so that is the opposite side of the spectrum, and that is basically the two lightest elements in the periodic table and the two most abundant elements in the sun. As a matter of fact, more than 70% of it is hydrogen, and about 27% of it is actually 72, probably. Anyway, they both of them combine to over 98% of the sun. For the most part, it's hydrogen. And hydrogen is really a proton and an electron when it's neutral. But the sun is hot enough, at least in its core, that this electron and this proton are separate from one another. So at the end, you have a bunch of protons floating in the sun and a bunch of electrons floating in the sun. Their number should be the same, okay? Because whatever proton, basically every hydrogen lost its proton. So at the end of the day, if you have 10 protons, you must have 10 electrons. Obviously, the number is much, much higher than this. So now the point I'm trying to say in here is that these charges are moving one way, the others are moving the other way. So it doesn't matter, the net current is moving in the same direction. So you have actually currents flowing every which way in the sun due to this big hot temperature and that of this gas that is a charged particle in motion, and charges in motion create a magnetic field. So the sun is a big, huge magnet. And the field lines, they twist and turn on each other, and where they twist and turn, sometimes they snap, and the field is trying to basically leave the sun, taking with a tremendous amount of energy, leaving the part of that where they left a little cooler than the rest of the sun, with several thousand degrees Kelvin, several thousand Kelvin less than the rest of the sun. Those regions become dark because they're actually a little bit less hot than the rest of the sun, and they form the sunspots on the sun. So how many sunspots do you have? And when they start to converge on one another, that is part of the solar activity that we monitor on a regular basis, because that is a telltale sign of some devastating effects that can reach the Earth through the solar flares. So this is in a sense what's going on, at least in the sun, on its surface. Again, the sun is big, of course. You have huge diameter. So the Earth diameter is about 6,400 kilometers. Radius is about 6,400 kilometers. So this is the radius of the Earth. Okay. The sun's radius, though, is 696,000 kilometers. So it takes more than 1,000 Earths lined from end to end to fill a radius. No, I'm sorry, 100. What am I talking about? Because 600 divided by 6,000 is 100. So it takes about 100 Earths, line them one to one another, to fill the diameter of the sun. But then on the other side also, there is another 100. And on the vertical side, there is another 100. In every direction that you choose, there is another 100. In all directions. So at the end of the day, 100 times 100 times 103 times is 1 million. 1 followed by 1, 2, 3, 4, 5, 6 zeros. So 1 million times the Earth size. So you take 1 million Earths and you put them compactly one next to one another, and you will form the sun. So it's a huge structure relative to the Earth. Okay, and it relieves tremendous amount of energy. If you guys remember when we discussed the energy that is released per unit area per second is 5.67 times 10 to the negative 8 times the temperature to the power 4. The surface temperature of the sun is about 5,800 Kelvin. So you take this number and you multiply it by itself 4 times. That's what the power 4 means. And you multiply it by this tiny number. It's still a big number, by the way, because you have here 10 to the power 3, 10 to the power 3, and 10 to the power 3, and 10 to the power 3. That is 612, so it's 10 to the power 12 plus times 6 times 6 times 6, so it's 36 times 36, so it's far more than 10 to the power 12, and that will kill this number. But again, this is how many joules are released per second, not all the time, not any other time. It's per second, per square area. The sun is not a square meter. The sun is so big compared to the Earth. It's about 1 million times the size of the Earth in terms of the physical size. So what you got to do in this case is you have to multiply that by the volume, by the surface area of the sun, which is 4 pi times the radius squared. And the radius in here is that number I was talking about, 696,000 kilometers. Convert that to meters. So it's 696 million meters. Square this number, multiplied by 696 million, and times 4 pi. That's how you find the area. So you multiply this number by itself, and you multiply it by 4 pi, and then you will find how much energy is being released by the sun. Tremendous amount of energy. It could not be explained by any other process than nuclear fusion. In other words, a proton and a proton will combine, actually 4 protons will combine to form helium, and they release a few other things. They release 2 positrons, which are electrically charged positives, and they'll release actually neutrinos, and they release energy, and there is all kinds of things, okay? So the point being in here is this is how, in a nutshell, what the process is. Actually, we're going to get into it in the next unit to see more details, to explain how the energy, this amount of energy, is released by the sun. Well, the surface of the sun has this granula that forms on its surface, this bubbling that forms on its surface, with dark spots that form on it, okay? And this is the so-called granules, I should say. These are the bubbles that form on the surface. And this region is the photosphere. This is the one that we see from the sun. This is the region of the sun. This is the one I was talking about, that it's about 6,000 Kelvin or 5,800 Kelvin, its temperature. So this is the surface of the sun. 5,800 Kelvin, if you do use the other formula to find the wavelength that maxes around this one, you should see it around the green. What is it, 10 to the power 6 divided by this temperature, which is 5,800 Kelvin, and this unit is going to be in nanometers for the maximum wavelength. This is Wien's law. This is from the previous units that we've been talking about. Again, see, these are some facts about the sun. The distance from the Earth to the sun is about 150 million kilometers. This is how we find it. The radius of the sun is about, I mean, I know I gave 696, that's more precise than 700,000. And here it's 7 times 10 to the power 5, which is 700,000. Actually, the number is a little less than that, but it doesn't matter. 600,000, 696,000 or 700,000 is very close from each other. The mass of the sun is about 2 times 10 to the power 30 kilograms, about 1,000 times bigger than the mass of Jupiter, which is about 1,000 times bigger than the mass of the Earth. The density of the sun is a little less than 1. I mean, little more than 1, actually, I'm sorry. And it's a lot less than that of the Earth, okay? If you know the mass of the sun, which you can deduce just by using Kepler's laws, basically take any planet as it revolves around the sun, find the period, and find the time, and the constant proportionality is actually relates to the mass of the sun. So you can measure those two values, P and T. From here, you can calculate. And for those sitting in Astronomy 125, namely the lab version of it, this is the technique we use to find the mass of Jupiter when we track the mass, the path of Io and Europa and Ganymede and Callisto. And we were able to determine the mass of Jupiter. In a similar fashion, you can determine the mass of the sun using any of the planets that revolve around it, then you can find its mass. That's how the number basically was found. This is modified from Kepler's third law. And this is from angular sizes, so we were able to find its radius. Take the mass divided by the volume. The mass is 2 times 10 to the power 30 divided by the volume, which is 4/3 times pi. Those are just numbers. It's like 4. It's slightly more than 4, actually. Times the radius square cubed times this number cubed. 7 times 10 to the power 5 cubed, which means that it's what? 7 times 7 is 49. Times 7 is about what? 7 times 5 is 35. So it's about 350, slightly less than 350 times 10 to the power 15. But that's kilometers. We have to multiply that by another 10 to the power 9 to convert it into cubic meters. Okay? 10 to the power 3 times 10 to the power 3 times 10 to the power 3, that's 10 to the power 9. So it's 10 to the power 21. No, I'm sorry, 24 plus these 2. So it's 10 to the power 24 and 2. It's 10 to the power 26. And the answer needs actually to be in kilogram per liter. So if it's a liter, then I have to do another conversion here. So I found it in cubic meters. And in a cubic meter, there are 1,000 liters. So you can do the conversions in here. You find the answer the way I'm doing it in actually a kilogram per cubic meter. Okay. Which should be a big number, relatively speaking, should be about 1,400 kilogram per cubic meter. Obviously, cubic meter is a very big volume. This is what a meter look like, okay? Roughly, it's about this size. So you take this much, and you take it in all directions, and that is the volume we're talking about. That's about 1,400 kilograms, okay? That's nothing really compared to, I mean, compared to the Earth, which is the same cubic meter, is about 5,000 kilograms, 5,500 kilograms, 5 tons and a half, metric tons that is, versus a little over a ton in here. So the sun is a lot lighter than the Earth in terms of density, okay? The central density is much, much higher though, because of the pressure that is from everywhere, okay, coming from the sun. The surface temperature I mentioned, it's about 5,800 Kelvin, but the inner temperature is much, much hotter. It's 15 million Kelvin, and you need this temperature to understand the processes that are going on inside the sun. Okay, 71% of it is hydrogen, and 27% of it is helium, and the rest 2% is just the remnants of the other elements. If you use this formula, the one I was mentioning earlier, on how to find the power that is generated, okay? If you use that formula, 5.67 times 10 to the negative 8 times the temperature squared, and the temperature to the power 4, I'm sorry, 58 times 5800 times 5800 times 5800, 4 times, and then you multiply that by 4 pi times this radius in meters squared. This is how much power the sun will output. Every second, the sun will generate 4 times 10 to the power 26 joules per second. That's what a watt is, okay? So this is called the luminosity of the sun. Down the road, this number is very important, and I really want you guys to remember it, because we're going to be referring to the sun as being of luminosity 1. So the sun will be our candlestick, if you wish, the one that we compare other stars to. So the other stars will have another luminosity. How many suns that is? Is it fraction of the sun if it's less luminous than the sun, or if it's more luminous, then it's going to have multiples of the sun. So the sun's luminosity will become our meter stick, just like when we use the distance from the Earth as being the one astronomical unit when you start measuring distances to Mars, for example, or for example, Jupiter 5.2 astronomical units, or for Venus 0.72. That means how far they are from the sun as compared to how far the Earth is from the sun. The same thing in here, when we're going to talk about luminosity of the stars, we're going to be referring to that of how much more luminous or less luminous than the sun with respect to this number. So we're not going to be plugging in numbers that are of the power 10 to the power 26 or 10 to the power 27 or so on and so forth. We're just going to give the number in terms of how it compares to the sun. But it's a lot of energy that is output per second, okay? No chemical burning. That's one of the assumptions that people, when they looked at this thing in here, they saw the sun, so they made, okay, what if it's wood that is burning? How much wood would you need? And you will find out that if it's really the entire sun was made out of wood, it would take only a few thousand years before it's run out of fuel, and then it's going to go dim. And indications were, even at that time, that the sun is much, much older than that, so therefore it's not a chemical reaction where burning wood would happen. So it must be another process, and the only process, as I said before, is nuclear fusion that can explain that, okay? The mere fact that it can explain it is not good enough. So if nuclear fusion can explain the output of energy that is coming from the sun, that is fine, but we need another reason to really nail it down. And I'm going to talk about that when we get into that unit. Anyway, the sun is made up of several layers. There is the photosphere that we're looking at, the one that we see from the sun. Outside of the photosphere, there is a chromosphere, and then there is actually another corona that forms in here. The temperature is much hotter, but the density is a lot less actually in this area. And then there is this region. Of course, you have this formations that we're going to be talking about immediately right now between the sunspots. So that's where the magnetic field lines basically take materials in and out, because again, as I mentioned before, they're all charged particles. So a charged particle inside the magnetic field will spiral, depending on its charge, will either spiral toward the north pole, or if it has the opposite charge, will spiral toward the south pole, and both charges exist in the sun. And then beneath that, there is a radiative convective zone, actually. And the convective zone is really what happens is, for example, when you take a pot, for example, of water, and you put it on top of the stove, and you see the bubbles form. So what's going on in this case is you have the upper layers of the liquid that are cooler than the lower layers that are in contact with the burner. So in this case, this is less dense, the one that is in contact with the burner, and it's hotter, so it rises because of its less density, and the one on top is denser, so it's going to fall in, and now the convection forms. This is exactly what's going on in the sun. There is a region underneath, below this region in here, in the convection zone, where it's in contact with the radiation that is coming from the core of the sun, and that is a lot hotter than the surface of 5800 Kelvin. So what's going on in this case is this is less dense than the one that is upper one denser. So now the bubbles form, and that's the granules that we were talking about in there. And that's how the sun gets rid of its energy. That's how this upper layer is actually maintains that temperature of 5800 Kelvin, because this region is much hotter than that. So there is a way for the sun to disperse some of its energy. Between the core and the convection zone, there is actually another region of radiation, okay, radiative zone or radiation zone. So here, the heat is so much from the core that the radiation will come out straight out, coming out in electromagnetic radiation. And it comes with extreme high frequencies for the most part, but then there are low frequencies. Inside the core, though, there are nuclear reactions that are happening inside the core, and those nuclear reactions, they produce tremendous high energy electromagnetic radiation, in addition to other stuff. Okay, we're going to talk about that. So technically, if we were just to be looking at the radiation emitted by the core, we will not be able to see it. The core will appear completely dark to our eyes because it emits in the high energy gamma rays. But because this radiation that comes out of the core immediately after the nuclear reaction encounters charges, among other charges, the proton and the electron. For the most part, it's actually the electron. So the radiation comes out of the nuclear reaction, which is extremely high energy, bumps into an electron, disposes some of its energy. In doing so, its frequency is actually lowered, its wavelength is a little longer. And this process continues for a long, long time, colliding, so that ray that formed, colliding several paths, several ways inside the core. It takes about 100,000 years inside the core before it actually leaves the core. So the radiation, the fact, I know today is cloudy, we don't see the sun, but if we see the sun today, that radiation actually was formed 100,000 years ago, long, long time ago inside the core of the sun. So it's completely opaque, basically, you can see nothing off of it. It's not transparent at all. And then at that time, so the radiation that comes out immediately from the nuclear reaction is tremendous high energy, tremendous frequency, high frequencies, extremely short wavelengths. We will not be able to see them. Then, by the time they emerge off of that, because of this scattering that happens with the electrons here and there, each scattering will cause them to lose more and more energy, lowering their frequency to a point where by the time and the wavelength is lengthened, so by the time they reach the outer layers, now they become in the range that we're familiar with, namely the light that we're familiar with, okay? So that's basically what's going on. Inside the core, the temperature is because of the tremendous pressures, and there is a law of gases that relates to temperature and pressure, and the law basically says PV equal to a constant. So if you do chemistry, you're familiar with this law. If you didn't, it's no big deal. So the volume times the pressure. So this is the pressure, that's the main thing. The volume is basically compressed it enough, so you can't really compress it anymore. So the volume is not really a big deal in here. This is a constant. So this is the number of moles, which is a constant, and here the number of materials inside the core of the sun. And this number is just another constant, 8.314. And this is temperature. That's the main thing. So the main thing in here from this relationship is that the pressure is high because the temperature is high, or vice versa, okay? So the temperature is high because the pressure is high, and the temperature is 15 million Kelvin, or 15 million degrees Celsius, about 27 million degree Fahrenheit, okay? It's tremendous pressure. This entire distance from the core to the photosphere is about 700,000 kilometers, about 100 times Earth's can be fit in that region, 100 Earths, okay? So this is the photosphere that we see. This is the outer surface of the sun that is visible to us. This is because the temperature is so high. This is in plasma. It's only about 500 kilometers thick, okay? Super thin. And then we're talking about that balance, and the balance basically has to do with the pressure from inside due to the temperature. So remember, the pressure times some number, which is the volume, is equal to some number times T. So these numbers don't matter at this point. This is the volume, this is empty. So as you go down more and more, the temperature is higher and the pressure is even higher. So the pressure here is higher than in here from the higher temperatures, because the temperature is higher near the core than outside. But then the force of gravity is less in this case because you only have this layer to contend with in the sun. Versus this point in here where you have the entire, both layers added up in here to help with. So at the end, it's the pressure due to this temperature and the inward pressure due to the gravity that balance each other, and you have a balance. The sun is not going anywhere. So if for some reason the sun swells, grows in size, so what happened in this case, the temperature through the volume increases, but then the pressure is lowered. So there is less pressure, that means less temperature, okay? But because there's less temperature, there is less pressure. So in this case, the sun must, because now gravity will win. Okay, so if it's worse, then there is less temperature, so now less pressure. So gravity will win and compress the sun further. And if it compresses it further, then the pressure increases. When it increases, the temperature increases, causing more nuclear reactions to happen, and that fight. So it's a balance. It's not going anywhere at this point, okay? As long as there is hydrogen diffused inside the core of the sun. This is the law that I was talking about. Pressure is some constant times temperature times density. The reason why it's written this way is the way, and most people know it, is PV equal to nRT, because N is actually the number of moles, which is related to how much the mass is. So I can write it as pressure is equal to N over V times R times T. If I change the number of moles, so the mass times the Avogadro number, so this whole thing changes in such a way that I will have the mass divided by volume, which is the density, times some new constant now, because remember I have to introduce Avogadro's number, times the temperature. So the pressure is a constant that is emerging from Avogadro's number and this other constant, the ideal gas constant. And then you have the temperature, and you have, of course, the density in here. Yes, the density changes a little, but that's not really going to be the main thing. Is the temperature and the pressure, for the most part, are proportional to one another. Okay, so that's what really provides the other side. Yes, gravity, we understand it. It's trying to compact the sun, but this outward pressure balances it so that the two kill one another. So that's basically how the sun retains its shape. How do we know all of this? We know it through seismic activity on the sun called helioseismology. Okay, so this is sun quakes, basically similar to earthquakes. How we determine the different layers for Earth in here. So we listen to them from distance, of course. So again, energy is transported through different ways. The first one is radiation, the second is convection, and then of course there is also contact, which is conduction. But the main thing are convection and radiation, and then radiation and convection, and then radiation again, because by the time it reaches us in here, it goes through a radiation process. As I was saying, it takes about 100,000 years for life to emerge from the nuclear reaction. So inside the core, you have now helium that formed, okay, when 4 protons came in and combined one another, plus some other stuff. We needed 2, because I lost 2 charges, 2 positive charges, because the neutrons now they are negative, they have no charge, and the protons are positively charged, so I lost 2 charges. So actually there are 2 electrons of positive sign that will emerge called positrons, and those 2, they will meet immediately 2 normal electrons, and they will cancel each other, and they will generate energy in the form of gamma rays, actually 2 gamma rays. And the same thing, I generate gamma rays in here. So I have a bunch of energy that is coming, and these rays are extremely high energy. But of course, we don't see that. What we see is actually more of a visible sun. If it were gamma rays, then we would not be, first of all, it's dangerous, far more dangerous than visible light. But then we will not be able to see the sun at all. So it's a completely dark region in the sun, it's opaque. That's the why? Because as the gamma ray leaves this nuclear reaction, it finds an electron, bounces off of it, and in doing so, its wavelength lengthens. So it finds another electron, and its wavelength is even further. and finds another electron, and it's imparts some of its energy to it, of course. That's how it's getting its wavelength longer and longer. So each time it finds an electron, it loses some of that energy and its frequency decreases, I'm sorry, and its frequency decreases. Remember, as the frequency decreases, the wavelength lengthens. I mean, I know this book uses the Greek letter nu for the frequency is equal to the speed of light. So if nu is going down, yes, then the wavelength is getting longer. So we're not dealing with gamma. So from gamma rays, we go to X-rays, and then we become in the visible region for the most part. We still have some of the infrared, actually, it's coming from the sun, actually, some of the UV, and even some of the X-ray, and some of the gamma rays that are coming, plus other waves also in the much longer wavelength region. But the point being in here is this is basically, this process takes a long time. The gamma ray that forms from nuclear reaction doesn't travel much at all. It travels without no distance whatsoever. It collides with electrons because it's so compact in that region. So it takes about 100,000 years for that light to reach us. So if something happens today, right now, in the core of the sun, let's say, for example, the nuclear reactions slow down, or they speed up. More hydrogen atoms now are colliding and combining to form helium. How do we know that? How would we know that if it were only up to light that reaches us from the sun? We will not know that based on light. We will have to wait 100,000 years for us to know, oh, something is going on. Something is weird is going on in the core of the sun. And those two things are called neutrinos. Actually, neutrinos, another byproduct in here. They have the symbol, same symbol as the frequency. So this is the frequency. Use the Greek letter nu, and the neutrinos, which are elementary particles of extreme low mass, and they don't interact with anything. They come straight out. So if something happens to the core of the sun, wait about a few minutes, about 8 minutes, and then you will know, hey, something is going on. Either there is an increase of neutrinos output or a decrease of a neutrino output. So you will know immediately. You don't have to wait 100,000 years. So that is really the idea behind this thing in here. Again, there is the solar atmosphere is made up of this extremely fine structure that looks like it's kind of a hair in here structure, kind of prairie gas in here called spicules, and that is because of a radiation that is coming from the sun. And the sun itself has all kinds of, I think we will have another unit dedicated to just this topic in here for the sunspots. We're going to talk more about them and how they form and what kind of things that you can do. Of course, the most damaging things are the CMEs. So what the coronal mass ejection is, sometimes you'll find it in the literature, CME is particles as this field line, because the sun spins around this one axis and it has this field line. So sometimes it's spinning faster into one region than the other one. So as it's spinning, one of them lags behind the other one, and the field line starts to basically entangle with itself, okay, and forms a region, figure 8, okay. So if this is the one sunspot, so a figure 8 will form, and that will snap. And if it does, then the materials contained in this loop, they will be ejected. And this is what the CME is. And those are charged particles. Remember, the charged particles are spiraling depending on the one side or the other. But now you have a bunch of charged particles extremely fast with a lot of energy leaving the sun. And this coronal mass ejections, they could cause a lot of problems on Earth. They could end civilization as we know it today. Those are, they will cause planes to fall down, they cause satellites to basically stop functioning, they cause cars, most of our cars are electronic anyway, they stop functioning, watches, electrical grid, everything basically is subject to their effect, okay? Heart devices inside people, so it's really dangerous stuff, okay? So anyway, this is this unit. Let me share with you the other unit. I know we started a little early today, so we're going to finish a little early too. And I know we have that exam coming down, so I probably should. Okay. So what's going on inside the sun? Basically, it's related to this relationship that Mr. Einstein has discovered. If you take the mass of the 4 protons, so these are 4 protons, and you take the mass of the helium that formed. Helium is basically 2 protons and 2 neutrons. So 2 of these protons, doesn't matter which, will change personality, and instead of being protons, they become neutrons. So they must each release an electron positive. So you have 2 of them that emerge. So those are called positrons. Positrons are electrons, except their charge is positive. So they carry with them the positive charge of the proton, and they change to become neutrons. Now, that is part of the story. Well, of course, these 2 positrons, they don't live long enough, because remember, the sun is beaming with electrons everywhere. So each and every one of them will encounter immediately an electron and will cancel each other. So they will actually annihilate one another. So at the end, we will have just energy coming off of them. Now, if you take this mass and you compare it to this mass, okay? So this is the after, and this is before. You will find that this mass overall is bigger than this mass. So before minus after is the difference in mass, or yeah, the difference in mass. So where did that mass go? It went to energy. So you multiply the difference in mass by the speed of light squared. Remember, this is 300,000 kilometers or 300 million meters per second squared. So it's going to be a big number. That is the energy. Every second, every nuclear reaction will generate, a tiny amount of energy, but overall you have a lot of particles inside the core of the sun that can cause this one. So this is the only explanation, as I was saying earlier, for the nuclear reaction. But being an explanation is not good enough. We really need to go for more than that. Okay? If this model, it's all it does, it explains what's going on in the sun, that is not good enough. So we really need to go a step beyond that. Okay. So what's going on in here, how this nuclear happens? Obviously, a proton will not interact with one another. Both of them are positively charged. So if you have a positive charge in here, this is positive E, by the way, it's the charge that is positive, and the other one is Q positive. So when you bring them closer from one another, they will repel each other. They don't want to be next to one another. Coulomb's law says that 2 positive charges will repel, 2 negative charges will repel. But if you give them high enough speed, because of the extreme high temperature, that's why the 15 million degree Celsius or 15 million Kelvin is required. So if they're moving super fast, they will overcome this barrier. They will have enough speed so that by the time, bang, they don't realize it, before they turn around, they are in contact with one another. And when they do come very close enough, here is the deal. 2 protons, they repel because of electrostatics. Tremendous pressure coming from force of gravity will cause them to come close enough. And if they come close enough, the nuclear force takes over. And nuclear force is 100 times stronger than that of the force of electricity. So here is the deal. So force of gravity, of course, brings things together. That's the one that gets things started. But it's super weak. It doesn't do anything. All it does is brings the material close enough. Okay. Now, close enough increases the temperature. And if the temperature increases, this particle starts moving fast to one another. When they are close by, the electrostatic forces, electromagnetism in general, because we're talking about both forces. Electromagnetic force, if you wish. Yeah, force due to electromagnetism will repel them. They will not let them stay, so going to cause them unless they come up with the right speed then they can overcome that force. Oops, where did I go? Okay, if they come with the right speed, then they will overcome that force. And if they reach a certain distance, minimal distance, then the two protons actually attract one another. Why? Because of nuclear force, nuclear strong force. So now they fuse. So you have a proton and a proton, and they fuse due to the nuclear strong force. So they fuse. Hold on. Sorry about that. Anyway, the point being in here is that, let me go back to the schematic because we really, it's a very, very important point so that you know that all forces are actually involved. And there are four forces in nature. It's not just these three. So by the time they fuse because of the nuclear strong force, which is 100 times stronger than this force, and this force is ridiculously stronger than the force of gravity. Okay. So they become too close from one another. Then, as I was saying in here, they fuse. So let me go and redraw this thing in here. So they become, because of the strong nuclear force, they fuse. But this is not stable. When you have two protons with one another, this is not stable due to another force, the fourth force in this case, and that is the weak nuclear force. That will change one of them, doesn't matter which, into a neutron. So you will end up with one of these protons going and becoming a neutron plus. Now it needs to balance the charges. This was positive E, this is zero charge. So now you need to get rid of that extra charge. So you have a positive that forms. Not only that, but there is a tiny particle in here that forms called a neutrino, okay, of type electron, a flavor electron, because of conservation of a lot of things in here. So this is actually called the baryon, and this is a baryon. So the baryonic number did not change. So I have one proton, one neutron, both of them are baryons. The charge also needs to be conserved. So the charge in here, I have a positive charge. Now I have still positive charge. So positive charge also is conserved. There is another conservation involved in here, called the lepton number. The lepton number in here is a -1. It's +1 for the electron, and it's a -1 for the positron. So it's a -1. Because I added a -1 in here, and I don't have anything from the other side, so I have to add a +1 in here from the lepton number. So everything is balanced now, so the equation makes sense. And those are what the nuclear physics predicts a positron that is going to form. This positron is short-lived. Immediately it's going to annihilate itself when it meets another electron. So this one is going to come out as a form of energy also. So this one, if you're counting on it, it's not going to tell you what's going on inside the sun because it's not going to travel far. It's this neutrino of type electron that is going to tell you the story of what's happening inside the sun. So if something happens today to the sun, this is the only way to know about it, through the neutrinos. Obviously, I formed another hydrogen because the number of protons and the number is still one. This is a heavier hydrogen called the deuterium. So this is the element that forms from this nuclear reaction. And this is not the final stage. So basically, the whole point in here, all four forces are involved. Gravity brings materials together, gives them enough speed so that the temperature increases. As that temperature increases, the repulsion will push them away. But if that repulsion is basically the speed is high enough, it can be overcome. Now the nuclear force, basically, so the electrostatic force is involved. Now the nuclear force will fuse them, But that fusion is short-lived because immediately one of them will change nature and become a neutron because of the weak force. So all the nature forces of nature are involved, namely gravity, electromagnetic, that is, electromagnetism, electromagnetic, and then now you have the strong, comes next, and the weak nuclear force. Both of them are nuclear forces. These are only the only four forces in nature. They are all involved in this case. So these are the keys in here. The deuterium is just this element, and then you have an isotope of hydrogen also. So this is an isotope of hydrogen, and this is an isotope of helium. An isotope of helium made up of 2 protons and a neutron. And this is the normal helium that we know it. Okay, so just this is so that you know exactly what's going on in here. So you have protons, neutron, and then the regular hydrogen isotope, the regular helium isotope, the odd helium isotope, helium-3, and the odd hydrogen isotope, namely H2. Okay, so here is the process. Starts with 2 protons moving super fast. And when they collide, they form this isotope of hydrogen, deuterium, okay, plus a positron, and which meets immediately an electron, and it forms 2 gamma rays, 2 radiations. And you need 2 because of the conservation of angular momentum. Only one of them will not do, okay? On top of that, you have a neutrino that comes out of this reaction. This deuterium will encounter another proton because there are protons all over the core in the sun. Now the proton will merge with the hydrogen, this isotope. So both of them are hydrogen actually, but one of them is a lighter hydrogen and the other one is a heavy hydrogen. So when they meet, in this case, they form this lighter version of helium, He3, and they release energy still. And this now is floating in them. This process takes very quickly. By the way, this process takes a long time to happen. And this one is immediately, okay? The process is expedited. Immediately, this one will encounter a similar one that formed on another path. So think of this one as it's mirrored from the other side. Now, 2 of them are coming together and they release 2 protons back to the mix in the core of the sun to be available, plus the helium. So now we have reached the end of the nuclear reaction. So what's going on in here? I have 1, 2, 3, 4, 5, 6 protons come in. 2 protons leave. So I have 1 and 2 protons leave. So I'm left with, out of the 6, I'm left with only 4 protons that mix. And these 4 protons, when they mix, they give me helium plus energy here, twice as much, energy in here, twice as much, times 2, because similarly on the opposite side, there is this much energy released, plus a neutrino in here, and a neutrino in here, which is also produced by this one. So there are 2 neutrinos. So in a nutshell, you have 4 hydrogen protons. When they combine, they give you a regular helium, isotope 4, so all of them are of the same isotope 1, plus 2 neutrinos of type electron, because there is different flavors of neutrinos. There are 3 flavors altogether. There is the electron type, and there is the muon type and the tau type, okay? So there are the electron type, because that's the only one that is involved in here. And that's going to raise another problem, by the way, there's types of neutrinos. Plus energy, because those gamma rays are just energy, that's all, okay? So that is basically, in a nutshell, what's going on inside the part. This process is called the proton-proton chain, not to be confused with another process happening in a much larger stars called the CNO, carbon, nitrogen, oxygen process cycle. So this is a chain, okay? It's happening in this fashion. Okay, how do we know all of these things about the sun and whether this theory is true? If we count the right number of neutrinos, let's say, for example, we come up with an estimate for how much reactions we have in the sun based on the amount that energy that is released, based on how much energy is released per nuclear reaction, because we can compute this one on a model. And we compare that energy that is produced based on the density, the temperature of the sun, we will know how much energy is needed per second to make the sun bright the way it is. So now at the end, I know how many neutrinos are produced. If I can detect the right amount of neutrinos, that would be great. So the early experiments, there was in Sudbury in Canada and another one in Japan called on Kamikandi, their laboratory, they did not produce this number of neutrinos. They produced the 1/3 amount that needs to be there. So the fact that you detect them is good, but you really need to detect the right amount too. So the first initial reaction was maybe we have the wrong model all along. Maybe that's not what's going on in the sun. Maybe there is a less rate of reactions going on inside the sun. Maybe the stories are going on inside the sun. So that was one of the issues that scientists were facing early on. But then they realized, as I was saying, there are 3 types of neutrinos. There is this type of electron. There is this type called the mu1 type, and there is the tau type. And what's going on when the sun produces this one, immediately they start fluctuating. So it's going to form enough of this, of the other 3 types. And at the end, the initial number is split equally between all of these 3 types. And now the reason why we were detecting a third is because of these fluctuations that is happening between the 3 different flavors of the neutrino. So this is called the mu1 type. And this is the tau type. And the one that I was referring to is the electron that is protein. And that's what the sun produces the electron type, by the way. It doesn't produce the other 2. But because the 3 flavors of neutrino, they fluctuate themselves between them. So if you have 10 of them, if you have 30 of them, for example, made, only at the end, 10 will appear as one flavor or the other. So that's why the early observations were detecting less than what should be, then everything is matches. So now we know the model is correct because it made a prediction and that prediction actually matches the observation. And actually now we know that this is what's going on inside the core of the sun. So this is the Kamikandi, I think the picture from it. This is the one that has so many detectors. Very hard to detect neutrinos, by the way. Extremely hard to detect them. And as they pass through this, sometimes they interact with the electrons, as I was saying earlier. And when they do, they produce a flash of light in here. So depending on the light that is produced in these LEDs, then the detection happens. And it happens, they have to bury the equipment way deep inside underground or under the mountains to eliminate all other sources of neutrinos, to just have the ones that are coming from the sun and be able to detect them when the earth is spinning around, so that you have day and night and the right number is the right number that is coming from the sun. The experiment is very delicate, took a long time to do it. Right now, I think there are the 2 major places that are happening. One of them is in North America, here in Canada, and another one in Japan. And this is I think there's another thing in South Africa or something. But this just gives you an idea of what's going on and how the sun operates and how we were able to detect these things. Again, these 2 units, first of all, what you need to take from is the structure of the sun, the temperature of the sun, the thermostat in the sun, the balance between the pressure and the temperature in the sun, the pressure and the gravity, I'm sorry, and then also the processes that are happening in the sun that can be justified, namely through the proton-proton chain. And that should be for these 2 units. Down the road units, I was going to open up more units than I thought because of the fact that we have exams this week, that we should focus on the exams. So let's focus on the exams. Let's get this exam out of the way. And then next week, when we meet on Monday, we'll have far more units, complete the sun, and then start with the stars. Okay. Please do take care of the review. It's going to be available until tomorrow night. And I will see you guys, not this Wednesday, because this Wednesday we have an exam, but I will see you Monday next week on the 14th. 14th, yes, November 14th. That's right. Yeah, okay. Yeah, that's good. Thank you. I'm going to stop the recording and I will see you guys next week. Also, please be mindful of the fact that you have several assignments on this week. I know I posted a lot of things. It's not assignments, honestly. It's more like stuff that is due from previous weeks, including your homework assignments. And I posted also helper for all of the homework assignments, the homework 4, 5, and 6. And I also posted, and don't forget, you have the project now that is due after the exam. A lot of things is due actually after the exam. So I will send more reminders for those. But right now, the focus is the midterm. Thank you.